Nature is famously lazy. It doesn't spend energy it doesn't have to. You can see this in how light travels. It always takes the path that requires the least amount of time. Biological structures instinctively follow this same logic. Look at this honeycomb. Bees build in hexagons because that specific geometry uses the least amount of wax while storing the maximum amount of honey. Nature achieves this efficiency automatically. But for humans to build systems that perform this well, we have to be deliberate. Efficiency isn't an instinct for us, it's a choice. This desire to replicate nature's efficiency is what drove Pythagoras to claim that mathematics could model the world. He believed the same logic that guided the beehive could be captured in numbers. The ancient Greeks, like Euclid, began mathematically proving how to find the best or maximum within a given shape. They were turning optimization into a formal science. You can see this logic in the legend of Queen Dido. Granted as much land as she could enclose with a single bull-hide thong, she formed a semicircle against the Mediterranean coast. It was a geometric proof realized in dirt and stone. The semicircle yielded the maximum possible area. But for centuries, this was as far as we could go. Optimization was treated as a manual, intuitive puzzle. The problem is that human spatial intuition is limited to simple shapes in 2 or 3 dimensions. To build a modern civilization, we needed to move past guesswork. We needed a universal language that could calculate the best result even when we couldn't visualize it. That language arrived with Al-Khwarizmi. He formalized the rules for manipulating variables, algebra, and gave us the first algorithms, or strict sets of rules for solving equations. René Descartes then mapped these equations to reality. By placing shapes onto a coordinate grid, as shown here, he turned physical objects into searchable numerical data. But systems are rarely static. They are defined by continuous change. Calculus gave us the tools to track that change and identify the exact points where a function reaches its highest or lowest value. In this topographical map, the objective is the lowest valley, the minimum. A data point calculates the slope, stepping down. At the bottom, the derivative becomes 0. The slope is perfectly flat, mathematically proving we've reached the optimum. We no longer needed to see the shape of the problem. Calculus allowed us to blindly feel our way to the best possible result, using mathematical gradients. During World War II, this process hit a breaking point. Logistics and resource allocation problems grew too massive for human brains to calculate by hand. Leonid Kantorovich and George Danzig developed linear programming and the simplex algorithm to navigate these high-dimensional problems. These were rules meant for a scale of math that exceeded human capacity. To execute these rules, we turned to the first computers. Room-sized mainframes, like the one shown here, handled the sheer volume of variables. They did in minutes what took mathematicians months. Machines built specifically to search for the optimum. We stopped doing the math and started building the engine to do it for us. Today, this process is so automated that a modern engineer rarely designs a final product. Instead, they design the parameters that the algorithm must follow. Here, the engineer defines 3 things: variables, objectives, and strict constraints. The algorithm then takes over, rapidly iterating through shapes, rejecting suboptimal designs, until locking on to a mathematically perfect wing profile no human would have drawn. This is the ultimate delegation. The human defines the sandbox, and the math explores every grain of sand inside it. Because we learned to frame our goals mathematically and automate the search for the best answer, we created the foundation for artificial intelligence. In 1997, IBM's Deep Blue used this logic to defeat Garry Kasparov. It evaluated millions of positions, optimizing its strategy one move at a time. This same lineage of algorithms is what allows systems like IBM Watson to parse millions of pages of data. They are searching for the most probable, most optimal inference. The quest that began with ancient geometry and bull-hide thongs has scaled into the digital age. The search for the best answer is now the core engine driving the neural networks of today.